All right. Hi, everybody. On this, right, today we're gonna look at our notes for acceleration. So the question that's kind of leading these notes is the slope of a position versus time graph, or sorry, is velocity. What is the slope of a velocity versus time graph? So this first statement we know from our previous notes, right? Go back to your position versus time note or the position versus time graph notes, and which is I think third one maybe. Let's see here. We talked about it here. So you can go back to there to take a look at that if you've forgotten about that. But what is the slope of velocity versus time graph? So the change in an object's velocity per unit of time, because it could be any unit of time, right, is defined to be acceleration. So basically, if you're changing your velocity over some sort of amount of time, we would call that an acceleration, speeding up, slowing down. Note that change in velocity can be positive or negative, so can acceleration. I do want to kind of note that we use the word acceleration in physics to be uh, speeding up or slowing down. So we don't use the word deceleration uh, for a couple of different reasons, but realize, and I'll go over this at the very end, realize that acceleration is any change in velocity. So it could be speeding up, it could be slowing down. So it doesn't necessarily mean that a positive velocity is speeding up and a negative velocity is slowing down because it depends on what direction you're going. Again, more on that in a minute. If we take a look at this, right, consider a velocity versus time graph. So let's say here's our velocity versus time graph for an object that's speeding up, right? The object starts at 4 meters per second and then increases its speed. So by the time we hit 6 seconds later, right, we're now going 16 meters per second. So we're seeing our, right, let's say this was the velocity of a car, it's going 4 meters per second, they step on the accelerator and they speed up to 16 meters per second. So right? That's obviously an acceleration. That's obviously a speeding up. And so the slope would be the rise over the run. So here we see it, right? The rise would be a change in velocity because, right, meaning going from 16 or from 8 to 16, right? Here we go. And then delta t would be, right, the run. So from 2 seconds to 6 seconds. So we can just see, right, this is just another way of showing you that the slope of this graph is the acceleration because delta v over delta t is the same as the definition from up here. Here we are calculating, right? Calculating it. The rise would be 16 minus 8 because 16 minus 8 over 6 minus 2. And that's going to give you 8 over 4, which is equal to 2 meters per second. So that meters per second squared are the units there. So there's that. Okay, let's take a look at the next page. So mathematically what that ends up being, right, if we take our y equals mx plus b equation, because it was a linear line, if you remember, the y would represent whatever the final velocity was. The slope is the acceleration. We just looked at that on the last page. On the horizontal axis, we had time plotted, so we'd replace that with the x with the t. And then the initial, right, the b, the y-intercept, would be the initial velocity, right? Because initially we were going 4 meters per second. So that would be the initial velocity, meaning the velocity you're going at the very beginning. So it's generally written this direction, this way instead, just I've flipped the AAT and the V naught. So that's the only thing that changes, but that's the way that I will be writing it. So let's take a look at our example problem here. So we have let's see here. A rocket accelerates at 15.5 meters per second. How long does it take to reach a velocity of 160? So it's going from, this is its acceleration, and then it gives us two different initial velocities. So it gives us an initial velocity of 0. So we can just write out, write out the equation that we were just looking at right here, and then we'll fill it in with the information that we know. So the reminder, the equation was v is equal to v naught plus at. final velocity is equal to your initial velocity plus how much you've changed your velocity by. So our initial velocity or our final velocity is to reach a final velocity of 160. So 160 is our final velocity. It tells us that we're starting from 0 for part A. It tells us that the acceleration is 15.5 meters per second squared. So the meters per second, right? Note the squared there. So that's going to tell me that's the acceleration. So that's how I can remember that this is the acceleration, because it puts the squared. Put that there. And we're solving for t. So of course the 0 doesn't really, you can drop the 0. And then we're going to divide by 15.5. And that's going to be 160 divided by 15.5. That's going to be 10.3, and that's going to be seconds is equal to t. So there you go. Hopefully that makes sense. So that means it takes 10.3 seconds to go from 0 meters per second to 160 meters per second, given that this is your acceleration, right? Meaning what this means is that you increase your velocity by 15.5 meters per second every second. So that's kind of what that means. Okay, looking at the next one, it's basically the same idea, except that now it's given us an initial velocity. So we'll just go ahead and write out the equation again. Right, our final velocity is still 160, just the difference is our initial velocity is 80 this time. So that just provides us one extra step that we have to do, which is to subtract the 80 from both sides. So that's going to give us, right, 160 minus 80 is 80. Still have the 15.5 t on that side. Divide by 15.5. 80 divided by, oh wait, 15.5 is going to give us 5.16 seconds. So that's the example problem. So the one last thing to add to this, right, is this kind of key idea at the end. And this is what I was talking about when I said I'd get back to this, right? So negative acceleration does not mean that the object is slowing down, right? And the reason is because if you're going in the positive direction, or sorry, your direction of velocity is in the positive direction, and your direction of acceleration is also in the positive direction, then you speed up. Remember, positive direction is often thought about like to the right. So if you're going to the right and you're accelerating to the right, then you speed up. If you're going to the right, to the positive direction, but you're accelerating to the left in the negative direction, that's going to cause you to slow down because these two are in opposite directions, right? You're going in the positive direction, but you're changing your velocity to be negative, more negative. So that's going to cause you to slow down, right? Obviously, the opposite is true if you're going in the negative direction, but you have a positive velocity, right? If you're going to the to the left, but then you're right, you're accelerating to the right, that's going to cause you to slow down. And if you're going to the left and you're accelerating to the left, that's going to cause you to speed up. You're accelerating in the same direction you're going. So hopefully that that kind of clears up some of this like deceleration stuff. So that makes a little bit more sense. So, okay, great. Thank you for watching. Those are your acceleration notes.